Great, here we go. Thank you everyone for joining today's session. My name is Ying. I'm from Microsoft. I'm engineering lead for Sonic team. Today we're going to talk about the evolution of the ToR technology in Microsoft in Sonic. So the agenda today is that we're going to take us through the past few years where we start to work on the ToR technology over Sonic. And we first introduced active standby technology with the ToR, and then we introduced active ToR naturally. And then I think that we believe that there's an endless possibility for the future, so we want to bring on paint a few pictures for everyone and call everyone for actions. So we have lots of pictures has been showing today or various sessions about the Azure topology, networking connectivity topology. I'm not going to go through that anymore. So from left to right, it's our traditional single ToR technology. And then in the middle, it's active standby ToR technology topology. And then at the very right, it's active ToR topology that we're going to most focusing on today. Of course, active standby ToR means that we do have two uplinks from the server to a pair of ToRs. Which we call them T0 and LT0. We used to call them UT0 and LT0 because it's on the rack. There's always one on the top side, on the upper side, and another on the bottom side, lower side. So the terminology comes from there. So over time, our operation team decided that hey, UT0 is not something we want to see. We have T0, so let's go back to T0 and LT0. We say okay, fine, we go with that. So with active standby ToR, if folks here have attended the sessions a few years back, the key part is a smart white cable, which has a MUX in the middle. The MUX job is to duplicate packets to going from the server side northbound to the ToRs, duplicate those packets to both ToRs. And the MUX is going to only taking one side of the southbound I/O from either of those two ToRs and forwarding it to the switch. Other side is not going to happen. All the packets coming down, if they ever coming down, will be dropped by the MUX. So that was illustrated by the dotted line, which is standby pass. And every single pass, every single connection of the three ends of this white cable has I2C bus controlling, connected into the white cable MUX part. So either side can swing the cable to either side. But in reality, we only swing the cable from ToRs. The server side never touch the MUX directions. So benefit of why we are moving to this active standby ToR topology is that we are moving the single point of failure further down from the ToR to a server side, right? To a single server or single white cable. It's easy to understand if we have a ToR crash in the old days with single ToR, every single server underneath suffers. But now if we, even if we have a ToR crash, as long as the other ToR is able to quickly react and pick up the slack, then the I/O impact will be minimal. So, and another benefit of this technology or topology is that the host has only one uplinks. Therefore, none of the application on the server needs to know there is a ToR topology on top of it. So it only have to enjoy the extra reliability that coming with the ToR topology. So of course, right? So all the engineer here is observing quickly that one of the link is standing by. So here comes $1 million question: why can't we use other link? Right. So the answer to that is active ToR that we're going to presenting today, and the active ToR is a generic solution that we put to the community, Sonic community. The full requirement specifications has been put out there. I'm going to go to some key points, but there is a chance that we can have a very, very generic solution to support dual ToR from the host side. So basically what's happening is that we have two uplinks from the server to both ToRs, and they can be active at the same time. That's, of course, the generic essence of active-active. And we do have to have a SOC on the server side or on the NIC side that help us communicating with both ToRs and let them to control the forwarding state of the uplinks from the server side. Right, so, and there is one more complexity that coming with this is that we are using a dark cable from either side of this, of both links are dark cables basically, right? So we don't have the I2C bus like we do have with active standby topology anymore. So the control protocol is happening in the same data path as the data plane. It is gRPC. I'm going to quickly touch on that later. However, the point is that if we lose the link, we also lose the control. So there is a need that coming from the other ToR, the peer ToR, to reach out to help in some certain scenarios. So a quick summary of the difference and commonality and differences between active and active dual ToR. Here's a quick comparison, right? So from the uplink view, the server sees a single IP, a single MAC, a single uplink, basically, more or less. And from the server, the sourcebound I/O to the server can come in from the either side of the ToR. When the ToR in standby mode for whatever reason, we are going to encapsulate the I/O hitting the standby side and sending over to the T1 again and coming down to the other active ToR and forward to the server. So for the T0 upfacing, we are going to advertise the same set of VLAN IPs. So from the T1 looking down, it looks like they have two passes to the same set of IPs. Same IP of the hosts, right? So they can do ECMP from T1 to T0. And from the server to ToR link, server is not going to see that very clear. For application, it's going to see that, but the link is standby versus active standby versus active, right? So, and the northbound I/O in the active standby scenario, we touch base a little bit. It's duplicate to both ToRs, and one of the ToRs needs to drop those extra I/Os in, so that we can prevent the duplicate packets sending to on the wire. But on the active side, I'm going to give you detail later, but we can transfer I/O. We can leverage both uplinks, so I/O is going to be dispatched to both uplinks at the same time, so we can use the full bandwidth of both links. The complication for that, of course, is that at the T1 level, you're going to see 2x of the I/Os coming from T0s because now both T0s are going to send active I/O up, right? So, of course, thanks to the community members here and lots of technology we touch base today, right? So we have to get T1 to T2 bandwidth doubled in order to saturate, in order to take this heat from the actual bandwidth from T0 to T1. And yeah, we talked about bandwidth already, and we already talked about the control, the cable control, briefly. So the I/O part, the key part of this active dual ToR is that we do have to have a way for both ToRs to understand the status, active standby status of those two uplinks, right? So there is a requirement that both ToR will be sending ICMP pings to the server side with a special target MAC range. And today, with the Microsoft solution, that FPGA, when detecting this special range of MACs, it will change the ICMP ping packet to ICMP reply, echo reply basically, and flip the source and destination IPs, and flip the source and the destination MACs, and then flip back to both links. The key point is that flip back to both links. With that, then both ToRs can monitoring the ICMP echo from either side, from both sides. So they both can know whether the peer is still alive and kicking. Right, so that is very, very important part. And the second important part, I touched base a little bit earlier already. In order to make sure that the T0 and the server are having the same view of those links in terms of forwarding status, we do need the NIC side or server side to have a special entity. In today's Microsoft solution, we have a SOC on the server side, host a gRPC server, and both T0s will establish gRPC connections to the SOC and tell the SOC to control the FPGA status, forwarding status. So otherwise, if both uplinks are healthy, then it is FPGA's responsibility to dispatch I/O per 5 tuples, basically. Excuse me. Dispatch I/O at stream level to both uplinks, so that we can leverage both uplinks and to its full potential. And we'll touch base on the T1 to T0 already, right? So because we are advertising the same set of IPs, target IPs to T1. So for T1, the server just have 2 passes coming down, so the T1 will naturally do ECMP as it is already doing today. And all the I/O will coming down will be distributed at stream level to either of the 2 T0s and get further forwarding to the server. So failure scenarios, it's interesting, right? So at the first, initially, everything is great, and both sides are active. And if one side of the link went down for whatever reason, cable get caught or whatever reason, right? So then if it's a link level issue, that link actually went down, FPGA and T0 will be able to detect immediately that this link is down. Therefore, they both put this side to standby. And as when this the T0 side link becomes standby, the T0 side will create a tunnel roads to put all the I/O targeting to that particular host to be forwarded to the LT0. And LT0 will decap those packets and then sees the same destination that is reachable from the T0 side and just forwarding to the FPGA, to the host side. Excuse me. So that's the second part that I briefly touched base a little bit, right? So then the LT0 side is going to learn from the ICMP ping. This is more or less a fail-safe mechanism, just in case if the other link stays up, but we still put it in standby. There's multiple reasons that could happen, right? One of the reasons could be the T0 put it in standby, but that's probably not the best example. But because in that example, if T0 side is going to put it in standby, and T0 side still have gRPC connectivity, then it has the capability of reaching out to the FPGA first and saying that I'm leaving, we need to put this link to standby, and they can have a consistent view, right? So, but in any case, if T0 side fail to do so, the LT0 side is going to say, hey, peer link is not healthy. I need help. So it will reach out and help set the FPGA side of the other peer link to standby, so that FPGA is not going to dispatch more I/O to the other side. So the link recovery detection is exactly the same reverse order, right? So we both sides determine that this link is healthy now, and they can be the link can take I/O again. So they will set the forwarding status to active again, and they start to leverage that link. So this is a quick decision table. Seems that I don't have time to go into detail. Basically, Another scenario has been called out here, basically that we don't if the T0 doesn't have any BGP connectivity to the T1, for whatever reason, could be all the link down, or could be just all the BGP sessions went down, then it will set itself to standby as well. Otherwise, uplink, any IO coming from the server to T0 will be black hole. So, of course, people is going to ask questions as why do we have to reinvent this dual uplink technology, given that we already have MC lag and such, right? So there's a few things that we actually analyzed this MC lag, and at that time when we started working on dual ToR topology, our determination back then was that this MC lag has its inherent issues or some difficulties, right? So one of them would be that you require this peer link to be existing, and there are some ToR goes out of sync, et cetera, et cetera. So there are some three-brain situations that it's really hard to recover from and really hard to detect. So that's why we decided to work on our own active dual uplink topologies for Sonic. So call to actions. As I went through a lot of the details requirements from the server side, so I see that there's a very good opportunity for us for the community to actually contributing or implementation a very similar so server-side implementation as what we have in FPGA and SOC to support gRPC, to support this ICMP deflection. With these two simple things, and of course, most importantly, the IO control, flow control, and IO flow dispatching. With those supports, there is an opportunity for generic, active support for the community, so everyone can take benefit for that. Yeah, we really want to see that happening in the future. And of course, we also want to see more varieties of the dual ToR-ready platforms. There is some certain level of ToR side requirements needs to be satisfied, right? So, but we have all the management tests ready, and we have all the details and requirements spelled out in the HLDs and such, and guarded by the Sonic management tests. So I think it's actually ready for the whole community to consume this technology and take more advantage. That's all I have today. Any questions, comments?
Could you have used EVPN multi-homing here? Because you don't need a link for that. You just need to peer between the two nodes.
Sorry, come again?
Could you have used EVPN multi-homing here? You just need, it's going to use tunnels too. You don't need the direct link. You just need to peer.
Oh, Jeff wants to take this?
So in any hyperscale cloud, overlay is run from the host. There's no overlay on the switch as such. There is a special VXLAN tunnel between up and down switch that's used in case of failure. Or actually in active in Libra case, it's used to transfer some traffic. But it's statically provisioned. There's no control plane. There's no infrastructure to run EVPN, right? And you can justify the complexity of VPN in reasonably simple underlay.
No, it's just a direct peer. I mean, there's a lot of complexity in the mechanisms here. It's not like, for most people, if they just ran a, direct peering between those two leaf switches, right?
But don't forget about scale. It's 10,000 switches.
No, you just need to do it on a pairwise basis. You don't need to do it across the whole thing. You just say, hey, these two switches peer. It's just simply, it's not for overlays. It's just for multi-homing.
So look end to end. In order to reach one another switch, you anycast, right? So both switches will advertise same SVI/26. I'm going into details. Will advertise same IP address upstream, so you can load share across them, right?
Exactly.
So if you start doing EVPN, you need to get everything else into overlay as well in order to reach those addresses. Meaning you need to deploy VPN at Microsoft scale.
All right, thank you.
Yeah, that's if you're doing the EVPN hop by hop and saying over the top.
So when we're talking about the multi-homing stuff, that's also brings some other complexities on the server side, right? So right now with this technology, we don't. None of the application needs to know any of those. It's treated as a fatter uplink, so to speak.
All right, great discussion. Thank you. Thanks for the presentation.
Yeah.